So one and all, I'm Aaswath, and today I'm going to be presenting on gas laws. So today we're going to cover the Boyle's law, Charles' law, Gay-Lussac's law, ideal gas law, and by combining the Boyle's law and Charles' law, we'll be getting the combined gas law as well. And we'll be working about case studies and all the laws based upon kinetic molecular theory. So we'll start off with Boyle's law first. Okay, so basically, Boyle's law states that the volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. So what that means is basically when the temperature of a gas is constant and when the gas is in a container, the pressure exerted upon the gas is inversely proportional to its volume. Now, so if you look at how it's derived, how the equation is derived, which is P1 is equal to P2, which is the equation of Boyle's law. How it's derived is basically P is as stated by the law, we can derive P is inversely proportional to V when P is constant. Now we know that if you want to make a proportionality symbol into an equation, we have to put a proportionality constant, which is the next one, is k, so which is P is equal to k upon V. Now, when we take V to the other side, it becomes PV, which is pressure in the volume of a gas, of a given mass of gas is constant. So, to make that into equation, P1 V1 is equal to K, and P2 V2 is also equal to K. So, in that way, P1 V1 is equal to P2 V2. Now, to better understand this, we'll be going through it with the on basis of kinetic molecular theory. So, what it basically states it. Okay, gases can be compressed because most of the volume of the gas is empty space. Now, what this means is basically gases have high intermolecular spaces due to low intermolecular force of attraction between each other. So they are very far apart. Now, when we keep them in a container, when we apply pressure on them, due to the large space they have between them, they can get compressed quite easily as compared to liquids and solids. Now, if we compress a gas without changing its temperature, so what's going to happen? So, when we compress a gas without changing its temperature, what's going to happen is the amount of volume a gas takes up is going to reduce. So, and the speed at which the particles move, which is the kinetic energy possessed by the when gas molecules will decrease as the amount of space they have to move also decreases. Now, to better understand this, there's a case study, which is there are two containers, both having the equal number of gas molecules, while one has more volume, but the amount of pressure applied is less, while one has less volume, but the pressure applied is more. Now, how we understand this is, in the first container, the amount of volume that the gases have to move is comparatively more than the second volume. So we can understand that the first volume has more pressure as compared to the second container. Now, first container has less pressure compared to second container. As the first container has less pressure, the amount of volume that a gas have to move is more, which is why they have high kinetic energy and the volume is more. And the second container, the pressure, the pressure applied on gas molecules is more, and the volume that they take up is less, which is why they have less kinetic energy. Which in turn proves that that more the pressure, lesser the volume, and lesser the volume, more the pressure. So shown that more the volume, lesser the pressure, while lesser the volume, more the pressure. Now next we are going to touch upon Charles law. Now Charles law's pattern is basically for a fixed mass of gas, the volume of a gas V is directly proportional to its absolute temperature. So what absolute temperature is basically? Absolute temperature is calculated in Kelvin of constant when at constant pressure. Now why we take Kelvin is because if we take Celsius, then it means that 0 degrees Celsius means the volume also has to be 0. But this is not the case due to many experiments. So it has been concluded that 0 degree Kelvin is when a gas molecule or a container filled with gas is going to be having a volume of 0. But as absolute 0 cannot be touched, it cannot be proved yet. Now the equation is basically V1 upon T1 is equal to V2 upon T2. Now how we derive upon this basically, according to the law, it states that volume of a gas is directly proportional to its temperature. So as such, V is directly proportional to T when P is constant. Now, to make any proportionality symbol into an equation, we add equal to and a proportionality constant, which I have taken as K. So from that we get the equation V is equal to KT. When we take T to the other side, it becomes V upon T is equal to K. Now to derive the equation like the previous one, V1 upon T1 is equal to K, while V2 upon T2 is also equal to K. So the equation comes V1 upon T1 is equal to V2 upon T2. Um, now, again on the basis of kinetic molecular theory, now volume of a gas, how is it related to temperature? So basically, when we touch upon kinetic molecular theory, the movement of particle or kinetic energy possessed by particles increases when temperature increases, which is why gas molecules, especially, they move more and they move frantically in all directions when temperature increases as the kinetic energy increases. Now, what this does is, as the amount of movement increases, the amount of space the same number of gas molecule takes up is more, which is why, uh, the amount of volume taken up by gas increases when temperature increases. As temperature increases. Now, to understand this better, we do to the case study. Okay, basically there are two containers. The first container has a lower, yeah. Okay. So basically, the first container has a lower temperature as compared to the second container. So how you understand basically, the first container has a lower temperature, which means that the kinetic energy, which is possessed by the gas molecules, is comparatively lesser than that in the second container, where the amount of volume required for the gas molecules to move freely due to the high temperature, which gives them a high kinetic energy is more. So so we can prove the Charles law due to the fact that a lower temperature gives the gas molecules a lower kinetic energy, which in turn requires for them less volume to move freely, while higher temperature gives them a higher kinetic energy, which in turn needs them, which requires more volume to move freely. Now, third one we want to touch upon is Gay-Lussac's law. So the verbatim of Gay-Lussac's law is basically the pressure of a given mass of gas at constant volume is directly proportional to its absolute temperature. So now from the law we can derive that P is directly proportional to T. That means pressure is directly proportional to temperature and the volume is constant. Now like the previous one, that to make any proportionality symbol into an equation, we are equal to and proportionality constant, which are again taken as K. So when we take T to the other side, P upon T is equal to K. And now to make it an equation, V1 upon T1, which is initial pressure and initial temperature, is equal to K, which is the constant. P2 upon T2 is also equal to K. So P1 upon T1 is equal to P2 upon T2. Now, on the basis of kinetic molecular theory, Gay-Lussac's law, which relates to pressure and temperature of a gas, can be explained simply with the kinetic one. Okay, imagine gas particles as tiny fast-moving balls. When you heat them increase temperature, these balls move faster and the container of the ball more often. Now, okay, the better example would be something like when we increase the temperature being exerted on gas molecules, they move more frantically apart. They move more frantically, more faster. But the thing here is they're not changing the volume. The volume is constant. So what happens is when the volume is constant, the amount of pressure being applied in the walls of the container, the gas molecules are present, that increases. Now why that increases? Because gas molecules are moving much faster with higher kinetic energy and they're colliding against each other, which in turn increases kinetic energy even more. Now next we are going to touch upon ideal gas law. Now what exactly is the ideal gas law? Now ideal gas law is basically, now I have stated three laws in the past. One is the Boyle's law, which is related to volume and pressure. Second one is the Charles law, which is regarding volume and temperature. And the last one was Gay-Lussac's law, which touches upon pressure, the relation between pressure and temperature. Now, what the ideal gas law is basically, there are as I mentioned three laws. There should be a law regarding the gases which can fulfill all three laws, or which is the relation between all three of the factors affecting a gas, which is pressure, volume, and temperature. Now, firstly, pressure, volume, and temperature can be calculated by various experiments. Number of moles is also can be calculated by the ideal gas constant, differs from medium to medium. So, what the ideal gas law is basically, it is PV is equal to nRT, where PV is pressure into the volume of exertion, pressure into the volume being exerted, while n is the number of moles, or the number of moles of gas that are being considered over here. R is the ideal gas constant, which won't be specified because it differs from medium to medium and can only be figured out through experiments. And last is temperature, which is the temperature of the gas. Now, this equation that I mentioned right now, which is PV equal to nRT, can only be fulfilled by those gases that fulfill the previously laws, which is the Boyle's law, Charles law, and the Gay-Lussac's law. Now, I already told you about ideal gas, but now we also know that there are a lot of factors coming into play when we try to calculate the volume, temperature, and pressure, and it's not always possible for a gas to fulfill this law, the ideal gas law. Now, what are those gases classified as? Those gases are called as real gases because they call, and it's not possible for us to acquire an ideal gas because when we calculate pressure, volume, and temperature at the same time, there are a lot of factors or variables coming into play, which is why it's not possible in the real world, and it's taking and this equation can only be fulfilled in the ideal world, as considered most equations at present. So, which is why this real gas. Now there are basically two stark differences between real gas and ideal gas. First one being, in ideal gas, molecules don't have any form of interaction, only kinetic energy. But in real gas, they have some form of interaction between each other, which is they have both potential, while at the same time they have kinetic energy. Now, as I've already mentioned, ideal gas, they follow all the gas laws that we previously mentioned, like the Boyle's law, Charles law, and Gay-Lussac's law, while real gas follows most of them, but not all of them at the same time, due to the presence of some variables. Okay, so okay, now we're going to touch upon Avogadro's law. Basically, so the verbatim of the Avogadro's law is volume is directly proportional to the number of moles of gas when temperature and pressure is constant. Now, what I mean by number of moles is the number of molecules present when we are considering when we are using this equation. Now, from the law, we can derive that volume is directly proportional to the number of moles, while pressure and temperature are constant. Like the previous one, if that is proportionality simple, we taking the equation, we add a proportionality constant, which I have taken as k. So from here, we can derive that V is equal to k into n, where k is the proportionality constant. Now, if we take n to the other side, the number of moles, so it's going to be V upon n is equal to T. To derive the equation from this, it will be V1 upon S1, which is initial volume by initial number of moles, which is equal to a constant, while V2 upon N2, which is final volume upon final number of moles, is equal to a constant. So V1 upon N1 is equal to V2 upon N2. Now, expression of Avogadro's law on the basis of kinetic molecular theory. Okay, so how do you explain this basically? Okay, yeah. Okay, so basically, let's take an example of two containers again. So one container, when one container has lesser volume, the second container has more volume. Now we want the temperature and pressure being applied at both of them is constant. Now what's going to happen is, if you take equal number of moles of gas, what's going to happen is this container will have more the gas molecules will have more space to move freely in, while this will be more while the other container or the smaller container with lesser volume will have less space to move freely in. So what's going to happen is basically, so how we can prove this law, how we can explain this law is basically, in the first container, which has lesser volume, which has enough space for the gas molecules to move freely without having any leftover space, while the second container, which has more volume, will have more moles of gas, which in turn will increase the number of molecules of gas present in the container, which is why all the gas molecules will have the same amount of space to move freely without any leftover volume. Now the last one will be the combined gas law. Now the combined gas law is basically when it is basically regarding the Charles law and Gay-Lussac's law combined together. So the reason, okay, so yeah, okay. So basically, what happens is, yeah. So from the Charles law, we get that V is directly proportional to T, and P is directly proportional to T from the Gay-Lussac's law. Now, it is known that A is directly proportional to B and C is directly proportional to B. This means that AC is directly proportional to B. So here we have V is here we
Different
have
color. Use different color.
from here we know that V is equal to D. V is directly proportional to D and P is directly proportional to D. So we combine both of them, we get V into P.
Yellow, yellow color. Use yellow color.
Yellow.
Yes, red is not.
Uh, so okay, A is directly yeah, so basically it's known that if A is directly proportional to B and C is directly proportional to B, then A into C is also directly proportional to B. So in this equation, when we consider B is directly proportional to D and B is directly proportional to D, we can derive B into P is directly proportional to D. Now from here we can get B into P is equal to KT. Now what I've written here is basically I've taken the T to the other side, which is why it's here instead of being with there. These are being multiplied volume. So when we take all of them to the all of them to one side and constant to another, the equation is going to be as such: pressure into volume upon temperature is equal to constant. From here, if this is a constant, then initial pressure, which is P1, initial volume upon initial temperature is equal to a constant. Then and final temperature into final volume upon final temperature is also equal to a constant. Then we have the final equation P1 P1 upon T1, which is equal to all these three are equal to a constant. So this means P1 V1 upon T1 is equal to P2 V2 upon T2. So these are the five gas laws that I mentioned. First we combine make combined gas law, and on the basis of the first three, which is the Gay-Lussac's law, Boyle's law, Charles law, we make up the ideal gas law.